The following KQED production was produced in high definition.
Before there were airplanes, before there were trains, there were sailboats. Without them, the world as we know it would not exist. Square-rigged sailboats brought Europeans to America. Their stable decks and massive holds carried the people and supplies that would build San Francisco. But these ships of old had their limitations. They were slow, and they only went in one basic direction, with the wind.
Square-rigged sailboats work by using sails as kind of more of a drag device than a lifting device, like a parachute.
A lot has changed. Today's sailboats apply very different principles to harness the power of wind and wave. So if you want to master modern sailboats, you'd better learn some physics.
So why did the wind shift? Just because?
The Quest team attempted to do just that on a recent sailing lesson at Modern Sailing Academy in Sausalito, California.
I think students, when they first come here, they know that the wind will push the boat because they see like a plastic bag being pushed across the street. So they can understand right away that the boat can be pushed, but what they have to learn is the boat can also go into the wind by using aerodynamics. Just like an airplane wing, the sail can lift the boat into the wind. So that allows us to go almost any direction we want to go, except for directly into the wind. Okay, hang on now, go straight. Go straight for just a second. You gotta get the boat speed back up. Just go straight for a second.
So modern sailing's not all about being pushed by the wind. Something is happening at the sail that makes it fly like a wing. And that elusive something is a force called lift. To help us understand what lift is, we've brought in some heavy hitters from NASA Ames Research Center who just happen to be avid sailors.
We call it lift because of the analogy to an airplane wing, I think. Well, now in a sailboat, that's all turned up on end, right? So now what we think of as lift is really, in our normal frame of reference, is a side force.
I think a lot of people don't realize that they are exactly an airplane wing just stood up on its side. And granted, it's a floppy airplane wing, but it works the same. When you want to get geeky about it, you can really start looking down at the nitty-gritty and really start learning a lot about how the sail works.
And here's the nitty-gritty. It's called a water channel, and it's one of the best ways to study how wings and sails generate lift. In this channel, filled with moving water, streamlines of fluorescent dye are injected upstream of a test shape. Although air is a gas and water is a liquid, both are considered aerodynamically to be fluids, so the resulting virtual super slow-mo image actually shows us how air would travel along the length of a sail or a wing.
Lights off. What I'm about to do is start introducing some glow-in-the-dark dye into the water. You notice that the streamlines on the lower side of the image are curving around the outside of the airfoil shape. Since those streamlines are curving, it has to accelerate a little bit. When it accelerates, it creates a lower pressure, and that's what actually generates the lift. And that lower pressure on the downside of the sail sucks the sail downwards to the bottom of the screen.
Essentially have high pressure on one side, and that higher pressure is trying to move toward the low pressure side and putting a pressure on the sail. That's from Bernoulli's law that says that the pressure forces and the velocity are related. You generate higher velocities on one side, so consequently there's lower pressure. Now you have the pressure difference, and that leads to the force.
Bernoulli's principle, named for 18th century Swiss mathematician Daniel Bernoulli, is pretty simple. Here's a way you can see it for yourself.
So I'm going to blow over a piece of paper that I'm holding in a curved shape, and we'll see what happens. So you can see how that lifts up. And that it completely relates to the flow acceleration over the curved shape and the fact that that higher velocity leads to lower pressure.
So as the wind travels along a sail, the sailboat's being lifted, or actually sucked, towards the curve of the sail, mostly to the side and slightly forward. But the wind generally hits the boat from the side, so why doesn't it just slip sideways? Because sailboats have wings above and below the water.
A sailboat, like anything dynamical, exists in sort of a balance of forces. The sail's above the water acting as a wing, and the majority of the lift that they're producing is in a sideways direction to the boat. Only a small component of that lift force is actually angled forward. Now, under the water, there's a keel, and as you move through the water, it's also developing lift. Its lift is predominantly sideways also.
In a modern sailboat, the keel and sail work together to move the boat forward. It's kind of like squeezing a watermelon seed between your fingers. Your fingers put equal sideways pressure on both sides, but the seed still shoots out in a forward direction. In a sailboat, the sail and keel's sideways forces cancel each other out, leaving only the forward force. That squeezes the boat forward, and bam, we're sailing. But as any novice sailor will tell you, it's harder than it sounds.
And in physics, they say you have a vector this way, you have a vector that way, and you have a resultant vector, which is the direction in which we are going.
It's tricky stuff.
It's tricky stuff, but it's fun. Because now
Okay, so we've captured the wind, and we're zipping along in the direction of our resultant vector. And that's all there is to it, right? Not so much. An experienced sailor knows that fine adjustments to the curvature of the sail, called trimming, make it possible to harvest the most lift and control its direction.
Okay, now look at our mainsail,
Yep.
and you see the little tails that were off the back of the sail. They've disappeared.
They're
They've
gone.
gone away. So what that tells me is we're not positioned the sail right to the wind.
Okay.
And so we're not getting the maximum lift out of the sail, and we're actually going slower than we can be going. Good. Now they're starting to come out.
Starting to see him a little bit more.
And now we have the sail properly trimmed for the course that we're on.
By trimming the curve of the sail, a skilled sailor is essentially shaping the size and location of the lift-generating area. By creating a deep, generous, forward-facing curve, a sailor can produce a large, well-directed pressure zone. But if the curve is too deep or the leading edge too abrupt, the air molecules flowing around the sail will stop following the curve of the sail.
When you put an object into a flow, the flow streamlines try to follow it if at all possible. If there's sharp angles in the flow particles are just not able to make that turn. They have too much momentum, not enough ability to get around the corner. And that's called separated flow. That would be stall in the case of an aircraft. It would be a luffing sail in the event of on a boat.
Okay, so if you want to learn modern sailing, there's a lot to think about. And as far as physics is concerned, we've just barely scratched the surface. But aerospace engineers like Steve Smith and Kurt Long live deep down in the details. For them, sailing is about the circulation flow field, viscosity theory, and starting vortices. And in these areas, even they don't always agree.
Oh my heavens, there's all kinds of controversies about sails. It's a very complicated subject. Many people, in order to get from point A to point B, don't need to know all of the intricate details of the sail. They just need to know from experience, when I do this, the sail works and I get from A to B.
Little swaggle, go!
My father introduced me to sailing when I was very young, probably 5 or 6 years old. My dad used to joke, and despite the fact he was also an aeronautical engineer as a career, he used to say that all this and a quarter would get you a cup of coffee.
Maine looks nicer than benches right now. You're looking good.
A sailor has an intuitive feel and a practical understanding that gets him by. And he doesn't really need to understand the detailed physics that much to be a successful sailor.
Pace is good here.
I'm working.
Well, perhaps you don't really need to know physics to operate a modern sailboat, but as the Quest team learned out on San Francisco Bay, a little understanding of how the sail and keel work can go a long way.
Keep Quest free. Discover more and donate at kqed.org/quest.